The use of non-metallic liquid-tight flexible metal conduit, or LFNC, with metallic conduit and conduit fittings is a violation of the National Electrical Code, or NEC. The NEC mandates that metallic conduit and associated fittings must be paired with metallic liquid-tight flexible metal conduit fittings to ensure a continuous electrical path to ground. This requirement stems from the fundamental principle of providing a reliable and lower impedance ground fault current path. The purpose of this path is to facilitate the rapid operation of overcurrent protective devices, such as circuit breakers or fuses, in the event of a ground fault. A ground fault occurs when an energized conductor unintentionally comes into contact with a grounded surface, such as the metal enclosure of electrical equipment or a metallic conduit system. Without a proper grounding path, the fault current may not be sufficient to trip the overcurrent protective device, leading to a prolonged fault condition. This condition can result in several hazards, including electrical shock, fire, and equipment damage. Metallic conduit systems, when properly installed, offer a robust and continuous grounding path due to the inherent conductivity of the metal. When a ground fault occurs within a metallic conduit system, the fault current will flow through the metal conduit back to the source. This high fault current will quickly trip the overcurrent protective device, isolating the faulted circuit and minimizing the risk of electrical hazards. Non-metallic liquid-tight flexible metal conduit, on the other hand, does not provide a continuous metallic pathway. Its construction typically involves a flexible non-metallic core with a liquid-tight jacket. While it offers flexibility and protection against moisture and corrosion, it lacks the inherent conductivity necessary for effective grounding. Introducing non-metallic liquid-tight flexible metal conduit into a metallic conduit system disrupts the continuity of the grounding path. In the event of a ground fault, the fault current would encounter a high impedance at the transition point between the metallic and non-metallic sections. This increased impedance would limit the fault current, potentially preventing the overcurrent protective device from tripping promptly. The NEC addresses the grounding requirements for electrical systems in Article 250. This article provides comprehensive guidelines for establishing and maintaining effective grounding and bonding systems. Section 250.4 outlines the general requirements for grounding, emphasizing the need to create a low impedance path for fault current return. Section 250.96 specifically addresses the bonding of metal enclosures and raceways. It requires that metal enclosures and raceways be bonded together to form a continuous electrical path. This bonding ensures that all metal parts are at the same electrical potential, minimizing the risk of voltage differences that could cause electrical shock. Section 356 pertains to liquid-tight flexible metal conduit. It specifies the permitted uses and installation requirements for this type of conduit. It is important to consult the latest edition of the NEC for the most up-to-date requirements. The specific sections and wording may vary slightly between different editions. Additionally, local electrical codes may impose additional requirements or restrictions beyond those outlined in the NEC. It is crucial to consult with the local authority having jurisdiction, or OJ, to ensure compliance with all applicable codes and regulations. Several factors contribute to the importance of maintaining a continuous grounding path in electrical systems. Firstly, it protects individuals from electrical shock hazards. A properly grounded system provides a low impedance path for fault current to flow back to the source, minimizing the voltage potential on exposed metal parts. This reduces the risk of electrical shock if someone comes into contact with a faulted piece of equipment. Secondly, it reduces the risk of fire. Ground faults can generate significant heat, which can ignite nearby combustible materials. A properly grounded system ensures the fault currents are quickly interrupted, minimizing the duration and intensity of the heat generated. Thirdly, it protects equipment from damage. Ground faults can cause damage to electrical equipment due to the high currents and voltages involved. A properly grounded system helps to limit the duration and magnitude of these fault currents, preventing or minimizing equipment damage. Finally, it ensures the proper operation of overcurrent protective devices. Overcurrent protective devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a predetermined level. For these devices to function effectively, they must be able to detect and respond to fault currents quickly. A properly grounded system provides the necessary fault current path for these devices to operate correctly. In addition to the NEC requirements, good engineering practice also dictates the use of consistent materials and conduit systems. Mixing metallic and non-metallic components can introduce potential compatibility issues. Different materials may have different thermal expansion rates, which can lead to stress and strain on the connections. Non-metallic components may also be more susceptible to damage from mechanical stress, ultraviolet radiation, or chemical exposure. The use of a properly sized grounding conductor within the raceway does not negate the requirement for a continuous metallic grounding path. The grounding conductor serves as a supplemental grounding path, but it is not intended to be the primary means of grounding the conduit system. The metallic conduit itself must provide a continuous grounding path to ensure proper fault current flow. While the installation of a properly sized grounding conductor is essential for electrical safety, it does not replace the need for a continuous metallic raceway system when using metallic conduit. The grounding conductor provides an additional layer of protection, ensuring that a low impedance path to ground is available for fault currents. However, the metallic conduit itself must still maintain its integrity as a grounding conductor. Consider the scenario of a fault occurring within a metallic conduit system where a section of non-metallic liquid-tight flexible metal conduit has been introduced. The fault current would initially flow through the metallic conduit until it reaches the non-metallic section. At this point, the fault current would be forced to flow through the grounding conductor. While the grounding conductor would eventually carry the fault current back to the source, the impedance of this path would be significantly higher than that of a continuous metallic conduit system. This increased impedance would result in a lower fault current, potentially delaying the tripping of the overcurrent protective device. Furthermore, the non-metallic section of the conduit would not be bonded to the metallic sections, creating a potential difference between them. This voltage difference could pose a shock hazard to anyone who comes into contact with both sections of the conduit simultaneously. In summary, the use of non-metallic liquid-tight flexible metal conduit with metallic conduit and conduit fittings is a violation of the NEC. It compromises the integrity of the grounding system, creating potential hazards of electrical shock, fire, and equipment damage. The NEC mandates that metallic conduit systems must maintain a continuous metallic grounding path to ensure the safe and reliable operation of electrical systems. Always consult with a qualified electrician and adhere to all applicable codes and regulations when installing or modifying electrical systems. Neglecting these requirements can have serious consequences. It is important to recognize that electrical codes and regulations are not arbitrary rules. They are based on years of experience and research, and they are designed to protect people and property from electrical hazards. Compliance with these codes is essential for ensuring the safety and reliability of electrical systems. When working with electrical systems, it is always best to err on the side of caution. If you are unsure about any aspect of the installation or modification, consult with a qualified electrician. Do not attempt to perform electrical work yourself unless you have the necessary training and experience. Electricity is a powerful force, and it can be dangerous if not handled properly. By following the NEC and other applicable codes and regulations, you can help to ensure the safety of yourself and others. Remember, electrical safety is everyone's responsibility. If you see something that does not look right, report it to a qualified electrician or the local authority having jurisdiction. Together, we can work to prevent electrical accidents and ensure the safety of our communities.